I'm Kinza with registration number 21TE03. Today, our topic in the discussion is adaptive filters. So, starting with a basic introduction of adaptive filters are dynamic systems that adjust their parameters in real time to optimize performance according to specific criteria. Unlike static filters with fixed coefficients, adaptive filters have self adjusting characteristics. Their weights or coefficients vary with time. Adaptive filters modify their coefficients based on the input signal characteristics and the desired output. The next question arises, what is the usage of adaptive filters? Adaptive filters are used in telephone echo cancellation, noise cancellation, equalization of communication channels, signal enhancement, and active noise control, etc. Their self adjustment capabilities make them highly useful in various applications such as noise cancellation, echo suppression, and system identification, etc. Next topic is need of adaptive filters. Adaptive filters are highly needed in various systems. For example, consider a linear time invariant system. This is a linear time invariant system. X of n is input and y of n is the desired output. The impulse response of this system is written as h is equal to h naught h1 up to h into L minus 1, where L minus 1 is the system length. These H are the system coefficients. If the system is linear time invariant, then weights or coefficients can easily be calculated. But if we have a time variant system where the weights vary with time, we need to calculate coefficients at each interval. So here we use adaptive filter algorithms. Our next topic is noise cancellation using adaptive filters. This is a diagram for a basic one-tap adaptive filter which cancels noise, and these are the equations which we have written by viewing this diagram. Y of n is the output of adaptive filter, E of n is the error which results from D of n and Y of n. D of n is the desired signal, which is a combination of original signal plus noise, and Y of n is the output of adaptive filter. And this W into n plus 1 is the weight, the weight or weight coefficients, and which keep updating. We have performed several iterations here. For n is equal to 0, we have put n is equal to 0 over in these equations all over here, and we have calculated the values of y, error signal, and likewise we have calculated the updated weights. Similarly, we can perform several iterations for n is equal to 1, 2, up to any number we want. So we have made a table. We have made a table for the results of the first 11 processed output samples, original samples, and filter coefficients values. After 7 adaptations, the adaptive filter learns noise characteristics and cancels the noise in the corrupted signal. The adaptive filter coefficient is close to the optimal value of 0.5. The processed output is close to the original signal. So the first 11 processed values for corrupted signal, reference noise, clean signal, original signal, and adaptive filter coefficients at each step are listed here. So in this example, we have observed that in environments where noise characteristics are unknown or change over time, adaptive filters can effectively reduce unwanted noise by continuously adjusting to signal and noise properties. And in telecommunications, adaptive filters help in cancelling echoes that can vary in intensity and delay, improving the quality of voice communication. Our next topic under discussion is Wiener filter theory. So the question arises, what is a Wiener filter? A Wiener filter is a type of a linear filter used to produce an estimate of a desired signal by minimizing the mean square error between the estimated and the actual signal. It is designed to handle noisy signals and is optimal for stationary signals with non-signal and noise statistics. The filter aims to remove the noise from the signal, preserving the important features of the desired signal. So this is a diagram of a system. This D of n is the desired signal, which is a combination of original signal plus noise. And here noise X of n is applied to a Wiener filter. Y of n is the filtered output of this filter. And these two inputs are applied here, and they produce a combined output where E of n is the error signal. So we have right equations here used by observing this diagram. E of n, the error signal, is results in the difference between the desired signal and the output of the Wiener filter. So E of n is equal to D of n minus Y of n, where D of n is the combination of signal plus noise and Y of n is the convolution of X of n and the coefficient of Wiener filter W of n. So we'll put these two equations here, and the equation of uh, the error probability becomes this. By taking scale on both hand sides, we get this equation. Here we will replace E square n to J, which is mean square error. We will replace D of n and X of n to P, which is cross correlation between both of them, and we will replace X square n by R, which is the autocorrelation of the noise signal, and we will replace sigma square n d square n by sigma square, which is the power of the corrupted signal. So the equation becomes this.